activities. Excuse me, I'm just getting over a cold, and I haven't lectured since December, so it's going to take me a little while to get my voice back. Anything else? Homework policy is the same. Everything else is the same. Note taking. So if you look at the schedule, and if you kind of look at the first page, I'm going to talk a little bit about how Physics 2 is different from Physics 1. First of all, most colleges and universities have one of two structures for physics. Physics 1 is always mechanics, which is what we did last semester. Kinematics, dynamics, Newton's laws, conservation of momentum, conservation of energy, a little rotational stuff, and that's pretty much it. Some colleges and universities pack everything else into Physics 2. That includes fluid physics, thermodynamics, and electricity and magnetism. And in a lot of places, also optics. Light and mirrors and lenses and how the eye works and stuff like that. A lot of places have a 3-semester sequence. My college that I went to, all of this stuff, fluid, thermodynamics, and optics, was all in Physics 3 with a little bit of maybe modern physics, relativity. We actually did a little relativity in Physics 1. Little quantum mechanics. And their Physics 2 is all electricity and magnetism. I actually like that better, but I think fewer and fewer. That's kind of an old-fashioned model, the Physics 1, Physics 2, Physics 3. And I think the reason a lot of universities moved away from it is because if you take physics for 3 whole semesters, you don't really get to the upper level stuff until you're a second semester sophomore or even a first semester junior. And that means it's harder and harder to get the upper level physics stuff in. So most colleges and universities use the model that we are using here. It's the same as William and Mary, it's the same as VCU. Mechanics in Physics 1 and fluids, thermodynamics, E&M, and whatever else you can squeeze in Physics 2. I can tell you right now we're probably not going to get to optics unless we really, really go fast through fluid physics and even faster through thermodynamics. I could do it, but I would have to really skim through the first 2 sections of the book. Just conceptually speaking, if you think about what Physics 1 and Physics 2 are about, Physics 1 goes from sort of Galileo, say around the year 1600, up through Newton, 1687, and to the idea of energy, which maybe takes you up to maybe the early to mid 1800s. Maybe we'll say 1860. Well, I don't know. If you don't do thermo, it really only takes you up to around 1800. Fluid physics, if we look at someone like Daniel Bernoulli, these are guys whose dates I don't know as well as I should, but you're talking about 1800s, or maybe around 1750, to say 1899, just before we start modern physics. And the difference between sort of what people were concerned with and the way we frame physics in these 2 eras is actually really, really sort of important and interesting. In Physics 1, everything was about point particles traveling on trajectories through space and time. Okay? You have a ball, it's flying through the air, you want to know where it's going to land. You have 2 balls with particular velocities, they collide, and you want to know how they're going to bounce off of one another. You've got the Earth going around the Sun under the influence of the gravitational force, and you want to compute that orbit and that orbital velocity as it moves around the Sun. You're usually dealing with a small number of objects with defined locations in space, x, y, and z coordinates, and Vx, Vy, and Vz velocities. And you're computing a trajectory for a few of those particles. If you look at what Physics 2 is concerned with, It's a very different sort of situation. In physics, too, most of what you're dealing with are things that are continuous. Okay? A continuum is some entity that has a value at every point in space. If we're talking about fluids, we're talking about things like gases, and we're talking about things like flowing water, water flowing through a pipe. That is not a single object with a single position and a single velocity. The gas inside a balloon is made up of trillions of trillions of trillions of gas molecules. We have no hope of describing the gas in a balloon by describing what every single one of those Avogadro's number worth of molecules is doing at every point in space. When water flows through a pipe, we don't talk about the individual velocities of every H2O molecule. That would be crazy. Instead, we consider the gas and the fluid to be continuous things that occupy space, that have a velocity at every point in space. But we have to learn how to treat that continuum of velocities at every point in space differently than we might treat a velocity of a single object at a single point in space. When you talk about thermodynamics, the situation is the same. You have an object. My hot cup of tea today. I brought a cold bottle of water today instead of a hot cup of tea. A bottle of water is maybe, if I just took it out of the fridge, let's say it's 50 degrees. And the room is 72 degrees. And we talk about this thing called heat that will proceed to flow from the room into my water and warm it up. But heat is not a kind of stuff. It's not an object. What is heat? Actually, before 1800 or before 1750 or so, people thought heat was a kind of stuff. They thought it was a kind of substance called caloric. And what happens is the caloric material in the air leaks into the water bottle and warms up my glass. But we know that's not what heat is. Heat has something to do with how fast the atoms and molecules in something are moving. And again, we can't ever hope to treat every individual N2 molecule in the air and every individual H2O molecule in the water and know its exact velocity and its exact position at every time the way we can with a ball flying through the air or the Earth going around the sun. So we have to somehow talk about this heat energy as a continuum that has a value at every point in space, but is not tied to a single individual object. When we go to electricity and magnetism, we know that things can be electrically charged. You can take your sock out of the dryer, take your sweater out of the dryer, and then you can see sometimes an attraction, sometimes a repulsive force between them because of these things called electrical charges, electrons and protons and things like that. But we can't see those electrical charges. We can't describe what's happening in terms of counting up all the little extra electrons on your sock and knowing exactly where they are. There's trillions upon trillions upon trillions of electrons in a sock. Instead, what we do is we create this idea of something that exists at every point in space called an electric field. And that electric field is not a single object, that has a single location. It is a continuum in space that I can assign a value to at every point in space. I can say, what's the electric field here, 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 here. But in order to describe that thing, I need a little bit more sophisticated set of tools than just knowing F equals ma for one object, just knowing that this path is a parabola, or this path is an ellipse, or momentum is conserved in this collision. One of the things I need to do is describe an extended quantity in three-dimensional space. One of the things we will do around midterm is familiarize ourselves with the mathematical tools for describing extended things like a vector field in three-dimensional space. This gets us in the direction of what is typically studied in Calculus 3, three-dimensional vector calculus, and the calculus of fields in space. We won't quite do Calculus 3 in this class, but we'll be able to see it from where we are. In other words, we'll be able to see what Calculus 3 is about and why it's necessary when we get to the point of talking about electric fields. The point I want to make just with this little introduction before we get started talking about fluids and doing something a little bit concrete is that the character of physics really changes from the 17th and 18th century to the 19th and 20th century. And the things that physics is concerned with become a little more abstract and a little less concrete. In Newton's time and in the 1700s, we're thinking of everything in terms of these hard, impenetrable particles that have a definite position and a definite velocity, and we treat their interactions one at a time, or at most two or three at a time. In fact, one of the things that came out of the 1700s in physics is if you have two masses exerting a gravitational force on one another, you can compute the trajectory of that mass exactly and come up with an equation for that ellipse. If you add a third object and try to compute the trajectories of all three of these objects as they pull gravitationally on one another, something called the three-body problem, it was actually proven in the 1700s that this is impossible to solve. In other words, if I want to compute an equation for the trajectory of one of these three bodies, I will find that doing that is impossible. Can't be done. Not just that it's really hard, it can be proven that no such solution, analytical solution, equation, can be found. And you might say, well, don't we compute the location of the moon and the planets all the time? We do, but we compute it approximately. We approximate it numerically. You can get a numerical approximation as close as you want. If I want to know where the moon is going to be in a month to within a mile or a foot or an inch or a nanometer, I can do that calculation. But what I cannot do is find an equation that is precise for every point in time. It does not exist. Well, if it shows I can't know exactly what three objects are going to do, I certainly can't know exactly what Avogadro's number of objects is going to do. I certainly can't know what's going to happen at every of the infinite points in space around an electrically charged sock. So the things we start to talk about and the tools we start to use in physics in the 18th and 19th century become a little more subtle and a little more abstract. The sort of distance between Newton's laws and something like a balloon full of gas or the idea of heat or an electric field becomes bigger and bigger and bigger and bigger. And as a result, I think conceptually Physics 2 tends to be a little bit harder than Physics 1, just because these ideas, these concepts, become a little more abstract, and because the relationship between the quantities and the math is sort of a conceptual step removed compared to as the kind of simple, here's a ball moving through the air that we do in Physics 1. That being said, the mathematics, at least for the first 2 units, for fluid physics and thermodynamics, is really not that hard. We're not going to be doing a whole lot of calculus problem solving in the chapters in fluid physics. We'll use calculus to prove Bernoulli's equation. We might use calculus to define the definition of entropy. Maybe I won't do that. But the mathematics is pretty simple, algebraic, plug in some numbers and get results. It's the conceptual stuff that's a little bit tricky. When we get to electricity and magnetism, though, the mathematical level steps up quite a bit. We will be using integral calculus a lot. We'll be using other coordinate systems other than Cartesian coordinates, and we'll sort of work through that slowly. If you look at the syllabus, you can see right around midterm, right after we talk about entropy and the second and third law of thermodynamics, we're going to devote a whole week to just talking about 3D coordinate systems, and then a whole week talking about multivariable integration, doing integrals in 2 and 3 dimensions, because that's really what you have to do in order to understand electric fields. So we're going to have a sort of dedicated math unit there in the middle. And this is probably, if you're going to go on to do science in some way, shape, or form, that middle section of the course is probably the most important part, sort of learning those mathematical tools. Yeah, so that's it. Any questions about what we're going to do this semester? Requirements? Okay, it's going to be pretty much the extension of last semester.
Professor?
Yes.
Do we use the same book as in class?
Same book. So if you paid for the license for G and Coley, that should still work. You shouldn't have to re-register anything. You shouldn't have to do anything new. It should all still be connected to Canvas, so everything should still work. I didn't put this page in the syllabus, but I actually spent some time a couple weeks ago really writing down a sort of philosophy of grading and what grades are for. And this really affected my decision to make the homework worth less and the quizzes worth a little bit more. Quizzes and exams are where you show me what you know. Okay? I know how to use these equations, I know how to solve these problems, I understand what the second law of thermodynamics are, and that's where I see that you know those things. Homework should really be for practice. Homework is really for you, and the quizzes and exams are really for me. And the only reason really for me to grade the homework and to score it is so that I know that you're practicing, and that you know whether you got the answers right and whether your practicing is paying off. So this semester I'm going to try harder to give more short homeworks, collect them more often, and get them right back to you graded, or get you solutions right back the same day. So you can expect to have homework every week, but it will probably only be 1 or 2 problems that I actually collect and grade. So for example, when we finish fluid physics, I might give you 3 or 4 practice problems and 1 or 2 problems that I'll actually collect and grade. So I won't even look at the practice problems other than to see that you did them. I mean, I'll collect them and say, yeah, you did these problems. Because what's important in kind of developing these skills is just doing the practice. But the grade is very, very small now because I made the decision to really focus on, and the educational word, and maybe I talked about this in the beginning of last semester, for assessment. And if some of you went to high school around here, you'll know these terms. There are 2 kinds of assessment in educational literature that teachers learn about education. They divide assessment into these 2 kinds of assessment: formative assessment and summative assessment. And formative assessment is supposed to be where the teacher sees how you are doing and has evidence that you are practicing these skills and getting better. And summative assessment is the thing you do at the end, which is to see what students know. And so your grade should be mostly this and very little that. The formative assessment should be for you to practice, for me to see that you're practicing, and for me to give you feedback and solutions to show that your practice is paying off. And then the question is, what are labs for? And this is something that I really struggle with. This is a lab class. We have lab every week. We don't do a lab every week, but we have lab every week. But when we do labs, what is that for? In some science classes, the lab is treated as, this is where you learn how to make a lab report, which is like writing a mini scientific paper. But I've never liked that because it's fake. It's not real. You're not really doing an experiment. You're testing Newton's second law of motion. We know Newton's second law of motion is right. You're not going to disprove Newton's second law of motion with these cheap carts and motion detectors that we have in this lab. So why do we do it then? And I think the real reason we do it is to connect connect the concepts with experience. And what the lab write-up should be then, to me, is a place for you to show that you understand the connection between the ideas we learned in class and the experience you just witnessed in front of you in the lab equipment. And yeah, they're not always going to line up. When you do a lab, you roll a cart down a ramp, your data looks like this. Maybe not that bad. X versus T. And there's two parts of kind of understanding what you just did. One is understanding what you should have seen if the world was the perfect world of frictionless planes and no air resistance, which is the equation distance equals 1/2 at squared for an accelerating object. And the second part is understanding all the things about the experiment you did, which complicate that, and what effect they would have. Things like air resistance and friction and uncertainties in your measurement and uncertainties in the data collection, equipment, whatever. And so it's the explanation of that disconnect. What should I have seen? What did I see? And what is the relationship between those two things? That is the important part, to me, of why we do labs. It's not the formal structure of a lab report. It's not that you know how to structure the abstract procedure, data, calculations, results. I don't really care a whole lot about that formal aspect of it. Although this semester I think we're going to gradually move to a point where by the end we're doing kind of a formal lab report just to say we've done it. Okay? It's about making that connection between the ideas that we talk about in theory and the practical experience. Because that's really what science originates from. Anyway, so the new grading percentages kind of reflect that division of labor between what the three different kinds of assignments are meant to do. And that was just a little thing that went through my head last week. And I think I'm going to write that up, that little sort of philosophy of grading, and start including it in the syllabus, because I think it's important, especially when it comes to the lab, for students to understand why they're doing what they're being asked to do. So let's actually start and do a little bit of physics today. Let's just define the term. Well, maybe we'll only go to 1:30. Let's define some of the terminology that we use to discuss fluids and fluid physics, and maybe derive one equation and then end with that. One word that I think we only used once or twice last semester is the word pressure. And pressure has a strictly mechanical meaning. When we talk about pressure in physics, I know I had a brand new black marker, and I don't know what I did with it. Pressure is a concept in physics that is related to force, and is related to when an object exerts a force on another object, the sort of way that force is spread out. If I take a pencil, I can take this pencil and I can take my hand, and I can do this, and it doesn't hurt very much. right? If I use this end of the pencil. But if I did the same thing with this end of the pencil, it would hurt a lot, even though the force is the same. What has changed between poking myself with the eraser end of the pencil and the pointy end of the pencil is the area, right? The area of the eraser is big, the area of the point is small, and the pressure is defined as the force divided by the area, the force per unit area. Okay. So if I'm exerting, say, 10 newtons of force divided by the area of the eraser, maybe a square centimeter, as opposed to 10 newtons of force divided by the area of the point, which may be a square millimeter.
The eraser is softer.
That has something to do with it also, right? The eraser has some give to it. So when I push on it, the force is exerted over a longer time, right? But even if instead of the pencil I used a pen, right, where both ends are still hard plastic, right, that still hurts less than that. So you're right, there's an impulse factor too, because the time is a little bit longer if the eraser is squishy. Now, if we lived in a simple world, we would always measure well, I'll just write it like this. Pressure in newtons per square meter. And we can measure pressure in newtons per square meter. But it turns out that pressure exists in a whole lot of other contexts. And each of those contexts has sort of its own vocabulary for how we measure pressure. And the other context that we talk about pressure a lot is with fluids. Now, one thing to remember this is not a good container to do my demonstration. So I'll just use this one. That's on purpose. It's for a lab we're going to do in a couple of weeks. When we talk about fluids, we're talking about both liquids and gases. So one scientific terminology that's a little bit different than the way we use the word in everyday life is fluids refer to anything that does not have a distinct shape that takes the shape of its container and that can flow. So usually in kind of everyday English, when we talk about fluids, we're talking about liquids, but fluid really means liquids or gases. Fluids exert pressure, but they exert pressure in kind of a different way than just poking yourself with a pencil or the amount of pressure you exert on the ground through your shoes when you're standing on the ground. When you have sort of a container of gas, and we ask how this gas is exerting pressure, that gas is exerting pressure outward in all directions. That keeps the balloon from collapsing. But there's also pressure being exerted this way. We know there must be because the balloon's not changing size right now. So if there's a force pushing out, there also has to be a force pushing in. And that's the air pressure, just the pressure of the atmosphere that we all feel all the time, but we don't really notice because it's a force that's always being exerted on us. So there's a force being exerted on every element of the area of this balloon, and that force can be quantified in terms of the force per unit area, or the pressure being exerted outward by the air in the balloon. If I push harder on the balloon pushes back harder. So if I do this and squeeze the balloon harder from the outside, that increases the pressure on the balloon. Likewise, if I have this container of liquid just sitting in this room, the weight of that liquid is pushing down on the bottom of the container. If I put it on the table, it's pushing down on the table. It's exerting pressure downward on the table. Does that pressure depend on the depth of the liquid? Does it depend on the size of the container? That's what we're going to talk about today. But there's also air pressure pushing down on the top of that liquid. So the pressure at the bottom is not just the weight of the beaker. It's the weight of the beaker plus the weight of the water plus the weight of all of the air on top of this container that's pushing down on the surface of that water. So pressure is actually kind of complicated. Okay? It involves air pressure, it involves fluid pressure, okay? And it doesn't just push in one direction. You know, if you've ever gone swimming and go underwater, that pressure doesn't just push down, pressure pushes in all directions when you are immersed in a fluid. That you can feel pressure pushing in on your ears. So the water in a container actually exerts pressure not just down, but in all directions. Just like the pressure outward in this balloon exerts a force outwards in all directions. One of the first things we have to come to terms with when talking about pressure is the units. And I like to start with this just to get it out of the way. The units that we use for pressure are ridiculous and crazy and complicated. Because some of them were designed to talk about air pressure, some of them were designed to talk about fluid pressure, some were designed to talk about pressures about the size of the atmosphere, some of them were talking about pressures of, say, a heavy object sitting on top of another object. So it turns out we don't actually use newtons per square meter as often as we use some other units of pressure. So the simplest unit of pressure we can use is the newton per square meter. Newtons per meter square. A newton per meter squared is also called a Pascal. Is that right? Yes. Okay. After Pascal did lots of the early physics experiments that are involving the first attempts in the 16 and 1700s to figure out what pressure was. It was actually a big deal. We kind of take it for granted nowadays that there's this thing called air pressure. But air is invisible. How do we know that air exerts a pressure on something? Some of the earliest real scientific experiments done by people like Torricelli and Boyle were experiments that showed that air pressure is a real thing. One of the famous experiments that was done is where they took two, and this was all made popular by the invention of the vacuum pump. They took two hemispheres of metal and put them together and sucked all the air out, or as much of the air as they could with 17th century air pumps, creating a vacuum inside, or close to a vacuum, not a perfect vacuum, but creating a low pressure area inside. And they put these hemispheres together and they sucked all the air out and they tied each of these hemispheres to a horse, and they had the horses try to pull the spheres apart, and the horses could not pull the hemispheres apart. Why? Because if there's no air pressure pushing outward, the air pressure of the whole atmosphere pushing inward is stronger than the strength of those two forces. And this established, first of all, that air pressure is a thing, and second of all, that it's possible to have a vacuum. And these experiments were done by Torricelli and Bohr and others. In fact, speaking of Torricelli, another unit. Well, let's go more slowly. The next, probably most common unit is the atmosphere. An atmosphere is equal to the average atmospheric pressure at sea level on the Earth. Now, obviously, this changes. It's not a constant of nature. When you hear the weather forecaster talk about a low pressure system or a high pressure system coming through, that means that the pressure of the air is going up and down by a little bit. But on average, an atmosphere is equal to 101.3 kilopascals. So 101.300. 1, 2, 3, no. Newtons per meter squared, or 101.3 kilopascals. And that's an atmosphere. That is almost the same, but not exactly the same, as a bar. A bar, as in barometer or barometric pressure, is equal to exactly 100,000 newtons per square meter. It's like an atmosphere rounded off. So 1 atmosphere is 1.013 bars. Bar. And then you've got your torr. A torr is related to a unit of pressure called a millimeter of mercury. A millimeter of mercury is equal to 133 newtons per square meter. What in the world is a millimeter of mercury? Well, one of the ways that we discovered that air exerts pressure and that there is such a thing as a vacuum is an experiment that was done by Torricelli back in the 1600s, where you take a pool of mercury, a flat dish full of mercury liquid, and you take a tube and you fill it full of mercury and you put it in there and upend it like that. And what happens is the level of the mercury always falls to about the same height. This was the first barometer, first pressure measuring device by Torricelli. When did Torricelli do this? Do we have the date? He lived from 1608 to 1647, so around 1640-ish. He was actually a student of Galileo. Evangelista Torricelli. Why is this always the same height? Because that is how much mercury, the weight of the atmosphere, which is what's holding this mercury up, can withstand. The mercury will fall until the weight of this on that much area is the same as the weight of the atmosphere pushing down on the rest of the pool of mercury.
Why does it have to be mercury?
It has to be mercury because mercury is really dense. If you could do this with water also, and the height is like 32 feet, right? So it's just harder to do the experiment. You use the heaviest liquid you can find. But Torricelli made barometers out of wine, and he made them out of water and all sorts of different fluids. In fact, if you want to know what it is for water, what is it for water? A millimeter of water Well, what is... let's see. Let me see if I can... 1 atmosphere in inches of water. Well, I typed that really poorly. Let's see if Google can understand that. So 1 atmosphere is 407 inches of water. We usually do it in feet of water. In feet of water. An atmosphere in feet of water is 33.8 feet. 33.8 feet of water is equal to 1 atmosphere. That means the weight of water pushing down on a container is the same as a column of water 33.8 feet high. What are some of the practical implications of this? One is that it is impossible to drink through a straw longer than 33 feet. If we made a 35-foot straw, and that's about maybe how far it is to the ground outside, and put a container of water down there, and put that 34-foot straw in there, and ran it up here through the window, and you tried to drink through it, you wouldn't be able to get the water up that 34-foot straw. Why not? Because how does a straw work? A straw works by you putting the tube in your mouth, pulling your diaphragm down to create a low pressure area inside your lungs and your head and your mouth. And what pushes the liquid up the straw is atmospheric pressure, pushing down on the top of the Coke or iced tea or whatever you're drinking through a straw. Atmospheric pressure can lift a column of water 33.8 feet high. The atmospheric pressure at sea level cannot push down hard enough to push water up any higher than that, push a larger weight of water than a 33.8 foot. Even if you could create a perfect vacuum inside your head, which obviously you can't, right? Your head would implode if you created a perfect vacuum inside your head. You could only do it 33.8 feet. In practicality, it's actually much, much less than that. That would actually be a nice experiment to do. Just go to Home Depot and get some clear tubing and see what floor of the building we can drink from with the amount of vacuum we can create inside of our heads. This was actually discovered by people digging mines, like mining for coal or mining for gold or mining for diamonds or whatever. When you're building a mine and you're digging these deep tunnels, they tend to fill up with water. And you build a pump to pump the water out, and it turns out you can't build a pump to pump any higher than 33.8 feet. Because the way a pump works, it creates a low pressure region, and it's the air pressure that pushes the water up. So if you dig a mine deeper than about 32 feet, you need to pump the water up in stages. You need to pump it up to a container here, and then you need to pump it out of that container to the top. Anyway, this is just kind of some random histories of how we discovered things about air pressure. But the point is, every one of these stupid units is used in physics. The millimeter of mercury is the same as a torr, T-O-R-R, named after Torricelli. So Pascal gets his own pressure unit, Torricelli gets his own pressure unit. There's the bar, there's the millimeter of mercury, there's centimeters of water, there's millimeters of water, there's inches of water. And obviously I'm looking all these up. I don't bother to memorize any of these conversion factors. Usually in physics problems, the thing we'll have most is pascals and kilopascals. Okay, those would be the most common. But often when you're given a problem, the problem setup will say such and such starts at atmospheric pressure or whatever. So you need to look up atmospheric pressure. You need to convert between the two. And I just go to Google and ask it what atmosphere is in kilopascal and let it tell me the answer. We probably won't see bar very often. And the only time you see millimeters of mercury, usually if you're doing something specifically about, well, that's not true. You'll see millimeters of mercury also. And you just have to remember to translate your units. It's not a big deal. Excuse me. So that's a little bit of history of pressure units, how the barometer was discovered. Let's just talk about fluid pressure and maybe call it a day. If we've got a container of liquid, it's pretty easy to guess at what the equation is for the pressure at the bottom of that container. Okay, if I've got a container like this beaker of water that has a certain mass and a certain area, let's say it's a circle, it doesn't have to be a circle, it could be a square, it could be whatever. We know that pressure is force divided by area, force per unit area. And we know that the force being exerted on the bottom of that container is just the weight of the water. And we know from physics 1 that the weight of something is equal to its mass times g. Newton's, we're not Newton's, the acceleration due to gravity. G is 9.8 meters per second per second. Now, because we're dealing with a continuous object like water, what is the mass of this much water? Well, I could put it on a scale and weigh the whole thing, but every container of water is going to weigh different. There is, when you're talking about a fluid, the thing that's constant for a fluid is not the weight, but the density. So the mass of this fluid is its density times its volume. Okay. Density, for which I'm usually going to use a Greek letter rho, is mass per unit volume. Go ahead and write that out. Mass. Okay. So the mass of that water is the density of that water times the volume of that water. The volume of the water is just the volume of the container. Whatever the volume of the container is, whatever the shape of the container is, as long as it's a right vertical thing. It doesn't matter if the bottom is a square or a hexagon. Or some kind of crazy shape like this. Oh boy, I can't do that. Not terrible. Whatever the shape is, as long as the sides are 90 degrees, the volume is equal to the area of the base times the height. If A is the area of the base, and H is the height, the volume of all of those shapes is the cross-sectional area times the height. And if you think about that, you don't believe that, think about it as a calculus problem, or to know the volume of this thing. The volume of a little slice is A times dH. You integrate all those stacks dH all the way up, and you get the height. So for the volume, we can write. So this is still the pressure, is equal to the density times the volume, which is the area times the height, over the area, and that area cancels out the numerator and the denominator. And we get that the pressure at the bottom of this container is rho g h. except we left something out. We just calculated the weight of the fluid in the container pushing down on the bottom. We left out the weight of the atmosphere pushing down on the fluid. So if we count that, then the pressure at the bottom of a container is equal to the pressure at the top, which in most cases is going to be the atmospheric pressure, plus rho g h. Sometimes you'll see that written as P0. If the top was not at atmospheric pressure, if it was some other pressure, it would be whatever that pressure is at the top. You have to be really careful in physics problems because when they ask for the pressure, sometimes they want you to count that pressure on the top and sometimes they don't. And your book goes through the difference between gauge pressure and true pressure. I'm not going to get into the nitty-gritty details of that, but it's something to keep in mind when you're doing a physics problem. Do they want the total pressure? Do they want you to count the pressure of the air? Or do they want you to just count the pressure of the water? Now, a couple of things about this. One, we have made an assumption. The assumption we have made is that the density of the fluid is constant. When we just said, well, the mass of this is just the density times the volume, that assumes that the density is the same everywhere. Is that true? Because after all, if you've got a bunch of liquid, isn't the liquid at the bottom, if we take an imaginary bit of liquid at the bottom, being pushed harder on by the liquid above it? Wouldn't that make it more dense? And the answer is yeah, a little bit. But it turns out for something like water, this difference is very, very small. Water is almost incompressible. So this is a good assumption for water. The density of water is pretty constant with depth. You can't actually compress water very much at all. That's why we use hydraulic pumps to lift really heavy things. If you push down on water in a hydraulic pump, that water pushes on the other side. It doesn't just squish the water. This is not true of air, right? If we think about the Earth, draw some mountains or something. Earth. And the atmosphere surrounding the Earth. The density of the air at the bottom of the atmosphere is much greater than the density of the air at the top of the atmosphere, because of the weight of the atmosphere pushing down. In fact, the density of the air at the top of a mountain is quite a bit less than the density of air at the top of the mountain. Did I say the same thing twice? The density of the air at the top is much less than the density of the air at sea level. That's why when we talk about an atmosphere, we say the atmospheric pressure at sea level. So this is good for an incompressible fluid. What would we have to do if it wasn't an incompressible fluid? Well, we would have to know how the density varies with height. And when we find the mass is not just the density times the volume. The mass is the integral of rho as a function of h dh from 0 to the top of the container. It'll be quite a bit more complicated. This is why, in physics, we often make the assumption that the fluids we're working with are incompressible. There may be some problems that we do where we throw away that assumption, but for the most part, we'll stick with that assumption. One more thing to add, and then we'll quit, is we assume that we're dealing with a container exerting a force on the bottom. That's not crucial to anything we just calculated. In other words, suppose I have a container that's very deep. And I want to know, what's the pressure here? In the middle of it. Well, the first thing to realize is that if nothing is moving, and the whole title of this section of the book is fluid statics. In other words, we're not dealing with flowing fluid, we're dealing with just fluids that are just sitting there. We know something about this fluid, which is if I take a little imaginary chunk of it, okay, just take some of the, actually just draw it as a dotted line. We take this fluid and we actually draw an imaginary cylinder in the fluid. We know that the net force on that imaginary cylinder of fluid is 0 because it's not moving. So the force pushing down on it and the force pushing up on it and the force pushing this way and the force pushing this way all have to cancel. Why isn't it falling? It has mass. Gravity's pulling it down. The reason it's not falling is because the pressure of the other water is holding it up. This leads to the conclusion that the pressure exerted by a fluid is the same in all directions. The pressure up and down and horizontally and on the sides of the container is all the same. Okay? Fluid exerts that force in all directions. Second, if I want to know what the pressure is at this point in the fluid, all I need to know is how much fluid is pushing it down from the top. So instead of having a real cylinder with height h, I can think of this imaginary cylinder where h is just the depth below the surface, and the calculation is the same. The pressure here is equal to the pressure at the surface plus rho g h. So that derivation we just did is not just good for the pressure at the bottom of the container, it's good for the pressure anywhere in the container. If h represents not the whole height, but just how far you are from top. Sometimes you'll see this written as a y, where y is the depth from the surface. All right, so the pressure is rho gh or rho gy. It's the weight of the air above the water, or whatever fluid this is, wine, mercury, whatever, plus the weight of just the fluid that's above you pushing down. And the pressure is what is holding that water up. Okay, so what we'll do next time is we'll work through a couple of problems, finding the pressure in different situations, looking at, say, what the pressure is on a submarine at the bottom of the ocean. And then we'll do some problems that involve a little bit of calculus. For example, suppose you're building a fish tank, and it's a rectangular box, and it has to hold a certain amount of water. How much force is being exerted on the glass walls of that fish tank? Well, it's not constant, right? The water pushing on the top is only this much water, the amount of water above that point. But the deeper you get, the more force is being exerted by that water, so you actually have to use calculus and integrate the force from the top to the bottom to find the total net force exerted on the walls of those aquariums. So we'll do some problems like that next time. All right, so we'll go ahead and cut it a little bit short today. This is the first day and my voice is already tired. And I will see everybody on Thursday.